In this lecture, we're going to introduce the Chenard-Larue transform, and we'll finish it in the next session. So now that we have learned spinors, we are ready for the SLR transform, or the Chenard-Larue transform, which is an invertible transform that relates an RF pulse to the Fourier coefficients of the alpha and beta frequency selective profiles that it produces. Earlier, we modeled continuous pulses as a set of weighted discrete rectangles, which allowed us to solve for the rotations that are produced by the pulse by concatenating the rotations produced by each sub-rectangle of the pulse. So the ith rectangle of the pulse produces a rotation theta is equal to minus gamma times delta t, the width of the pulse in time, times the strength of all the magnetic fields that are active during that time point. And this rotation is produced around a normalized vector n sub I, which is equal to gamma delta t divided by theta sub I times those magnetic field components. So the length of this vector is again 1. With this calculation of the rotation angle and the normalized vector, we can then compute the rotation parameters for each rectangle. So for the ith rectangle, we have the vector aibi, the spinor aibi, is equal to cos theta over 2 minus inz sine theta over 2. That's the A term. And the B term is equal to minus I nx plusiny times sine theta over 2. Same definition we used before. Then the overall rotation matrix for this time point is equal to AI minus BI conjugate BI, and then this should be an AI complex conjugate. So this is the rotation matrix for the ith time point of the RF waveform. The total rotation is then the concatenation of the rotation matrices for all the time points. So we start at 1, 2, 3, go up to I, and then go up to the end. So we call Q with no subscript the overall rotation produced by the entire pulse, and the cumulative rotation from time point 1 up to time point I we call alpha I beta I. This means though that we can also propagate forward an initial spinor as a recursion. So if we have an initial spinor, so for example if we start with no rotation, in which case alpha would be 1 and beta would be 0, we can get the next time point by multiplying the current spinor by the rotation parameters for the ith time point, and that gives us the spinor for the ith time point, after the ith time point. So this makes it simple to compute using this recursion, but it gives limited analytic or design utility. Okay, so then we need to, in order to actually enable the Chenard-Larue transform, we need to introduce the hard pulse approximation. So we get a tremendous simplification of these expressions if we assume that the RF pulse comprises a train of impulses, right? So instead of rectangular functions now we have impulses, which are separated by free precession intervals. Okay? So we knock a little bit of magnetization, and then we wait for phase to accrue during the gradients. Then we assume that no phases accrue during due to the gradients during the next RF rotation, and then we wait for phase, knock some RF down, wait for phase, knock RF down, wait for phase. So we refer to the periods during which the gradient is modeled as the free precession integrals. That is, we're not tipping the magnetization into or out of the plane with the RF. It's just accruing phase due to different sources of frequency offset. And in between those free precession intervals, we're performing the knockdown or knock-up with the RF pulse. So stated another way, we're interleaving the rotations due to the RF and the gradients so that they are not at the same times. Now the hard pulse approximation is a good approximation to a continuous soft pulse if the rotations are small. That is, if we use small enough deltas between the pulses, delta time steps. It is arbitrarily good if you sample finely enough in time. It was first introduced by Mayer Chenard, Jacquelet, and Patrick Larue. So we can take a zoomed in view of this, and we say then that theta sub I, the rotations due to the gradient, due to the RF, to each RF sample is gamma B1 of T sub I, the strength of the RF at that time point, times delta T. Note that B1 here is complex valued, in that it has an X and a Y component. And then the gradients rotations are also the same between each period, and that phase is minus gamma g x delta t. So these are constant. These are all the same. Sorry, I misstated this earlier. These are changing in time, but these are all constant. Okay? So the incremental rotation matrix for one RF impulse and one gradient rectangle is this cascaded set of rotations. Right? Since now they're happening at different points in time, we can split apart the rotation matrices. And that's what the hard pulse approximation does for us. So we have the rotation matrix due to the RF impulse. Note that because there's no NZ component to the RF impulse, C is now, the alpha parameter is now real valued, so there's no complex conjugate here anymore. And then the second diagonal matrix is the rotations due to the free or gradient precession. And more specifically then, C sub I is cosine of the RF rotation angle divided by 2. S sub I is now the phase of the RF, which determines nx and ny, times I times sine of the rotation angle over 2. And then Z, the free precession phase accrual, is equal to e to the I gamma gx delta t. This is a complex exponential that applies the phase due to the gradients during the free precession interval. So again, just to make sure this is clear, we note that for the RF, there's no NZ component, right? The RF is a magnetic field that lies completely in the transverse plane, and thus its nx and ny is equal to the phase of the RF. And we can illustrate this by calling the xy plane again a complex plane, where x is the real axis and y is the imaginary axis. So here's the RF field at this time point ti, which has real component b1x and imaginary component b1y. And then the vector around which we're performing the rotation is nx and y, which is equal to the phase, which is a vector that has the same phase as the RF. And the rotation angle is actually theta here in the previous notation. So if we substitute this expression where we've separated out the rotation due to the gradients and the rotation due to the RF into our previous recursion, then we have that the incremental that the spinner at time point I is equal to the spinner at time point I minus 1 times the precession that happens at time point I and the RF rotation that happens at time point I. Now note that we can factor out a z1/2 here in front of this, and this simplifies the free precession rotation matrix a little bit. For convenience, we want to get rid of the half powers of z overall, so we're going to define this a sub I, capital A sub I, as z to the I over 2 alpha sub I. Note that I here is not square root of minus 1, it's the time index. And bi is equal to zi over 2 times beta I. And if we make that definition, then ai/bi, the rotation up to a certain time point, is ci minus si complex conjugate si/ci. Note again the lack of a complex conjugate on ci because it's real valued. 1, 0, 0, z inverse times a I minus 1 and b I minus 1. And then again, our initial condition does not change compared to the standard spinner case. It's just 1, 0 corresponding to no rotation. Okay, so bear with me here. We're going to look at what the structure. We're going to look at what the structure of these expressions is. Okay, so to do that, we're going to multiply them out a couple times. So at the first time point, after the first rotation, we have C1 minus S1 complex conjugate S1 C1 times 1, 0, 0 Z inverse times 1, 0, which gives us C1 minus S1 complex conjugate S1 C1 times 1, 0, and that gives us C1 S1. Okay, pretty simple so far. In the second time point, we have C2 minus S2 complex conjugate S2 and C2 times 1, 0, 0 Z inverse times C1 S1. Okay, but that simplifies. Then we can combine the last two, the vector and the last matrix, to get C2 minus S2 complex conjugate S2 C2 times C1 S1 Z inverse, and then multiply that through and get C1 C2 minus S1 S2 complex conjugate times Z inverse C1 S2 plus S1 C2 Z inverse. And you notice right away that these are really polynomials in Z inverse, right? So this is the 0th order term and this is the 1st order term, if we think of these as polynomials. So what we have now are polynomials in Z inverse. And if we move this forward in time, at the nth time step, what we'll have is sum over j equals 0 to n minus 1 a sub n j z minus j, and the b sub n polynomial will be of the form j equals 0 to n minus 1 b sub n comma j z minus j. Okay, and these guys are two n minus 1 order polynomials in Z, where Z is equal to the rotation, incremental rotation due to the gradients. Okay, so we've transformed these rotations into two polynomials. Note here that the a sub n sub j, the a sub n j's are not the same thing as the a1 b1s, or sorry, the a sub n j's and b sub n j's are not the same things as the a sub I, b sub i's that you would get by propagating forward in time. They're the coefficients of the final polynomial after all the time points up to time point capital N. So the operation of calculating these coefficients for a given RF pulse is called the forward SLR transform. Okay, so to get the slice profile of a given RF pulse, we can use the SLR transform as follows. First, we evaluate the coefficients of the A and B polynomials recursively. Then we evaluate their values for given Z values that we plug in. And specifically, those values will lie along the unit circle, and we get the profile then by taking the DFT of the coefficients that we've calculated in step 1. That is the discrete Fourier transform, which we use the FFT to evaluate. And this corresponds to calculating the profile at a set of equispaced spatial locations or frequency locations, n delta x, which is equal to n over gamma over 2 pi g times capital T, where capital T is the duration of the pulse. So to see that what we have is a DFT here, we can substitute the definition of Z inverse into the and then these x locations into this complex exponential here, or into the expression for the polynomial for A. So we have both the definition of Z inverse and then we plug in the actual x values. You'll note here that G cancels, the gamma cancels and gives you 2 pi, and then delta T over capital delta, or capital T, is equal to 1 over n, right? Since delta T over T is 1/nth of the total duration of the waveform. And then we get a DFT expression. So we get e to the minus I 2 pi n times j over n, where j here is is like the time index, and n here is like the frequency index at which we're evaluating the RF pulse. And the same relationship, of course, holds for b sub n. So here, really, in this expression, Z itself is the DFT kernel. Then we can take the alpha and beta polynomials that we calculate by DFT and compute the desired profile that we're interested in looking at. So for example, MXY at these equally spaced spatial locations would be equal to the A profile that we get from the DFT, complex conjugated, dot times the B profile that we get from DFT, multiplied by 2. And then evaluated at Z, where Z has the complex exponential definition given here. Okay, so that's the forward SLR transform. Next time we'll talk about the inverse SLR transform.